we're getting ready to start section 5.4 on some formulas that you probably should put to memory. There are occasions when we can use these in calculus, probably more in calculus 2, but maybe not quite as much as like your double angle formulas and some of your Pythagorean identities and such. However, they are useful. You can use these to simplify expressions. You can use these to find exact values. You can use these in a matter of verifying an identity. So we're going to go over two different sets of formulas here. These both are derived, as it turns out, from the sum and difference formulas that you had in a previous section. So the first ones we'll look at is changing a product of two trig functions into a sum of two trig functions. Now I know it may not make a lot of sense to you right now, but this comes in really handy in integration in calculus. So we have the sine of alpha, sine of beta is equal to 1/2 times the quantity of the cosine of alpha minus beta minus the cosine of alpha plus beta. The cosine of alpha times the cosine of beta is equal to 1/2 times the sum, or the quantity I should say, of the cosine of alpha minus beta plus the cosine of alpha plus beta. This third one here, sine of alpha cosine of beta is equal to 1/2 times the quantity of the sine of alpha plus beta plus the sine of alpha minus beta. And this next one, the cosine of, fourth one here, cosine of alpha sine of beta is equal to 1/2 times the sine of alpha plus beta minus the sine of alpha minus beta. You can see how similar these two are because, of course, multiplication is commutative. And if you commuted these around, you would have the opposite expression here. And, of course, since sine is an odd function, that would just bring the negative out in front. So we're going to use these properties, or at least a couple of these, to simplify and rewrite these two products as a sum or a difference. Now the first one I have here says cosine of 6x, sine of 2x. That looks like number 4 here. So according to this formula, this would be my alpha, this would be my beta. This would be 1/2 times the quantity of the sine of alpha plus beta, 6x plus 2x, minus the sine of alpha minus beta. That'd be 6x minus 2x. Of course, this is 1/2 the quantity of the sine of 8x minus the sine of 4x. And if you want to distribute through by the half, you can. But there we have changed this product into a difference. Now this one down here, the cosine of 4x, cosine of 5x, that looks like I'm going to use formula 2 here because they're both cosine. This would be my alpha, this would be my beta. So using this formula here, this is going to be 1/2 times the cosine of alpha minus beta, so that'd be 4x minus 5x plus the cosine of alpha plus beta, that'd be 4x plus 5x. Now this is 1/2 times the quantity of the cosine of the opposite of x plus the cosine of 9x. And there's nothing really wrong with this except that you should know that cosine is an even function and the cosine of opposite of x is the same as the cosine of x. And there's my expression. And again, you could distribute through by the half if you chose to. Alright, next one up. We're going to use one of these formulas here to find an exact value. Now I know you could use some of the other formulas that we've already dealt with, half angle, sums and differences, but we're going to use one of these product to sum formulas, and we're going to rewrite the sine of 165 degrees, cosine of 75 degrees, and get the exact value. So in this case, it looks a little bit like number 3 here, because you have the sine first, and then you have the cosine second. So we're going to use number 3 here. My alpha is 165, my beta is 75. So this is equal to the sine of 165 cosine of 75 degrees is equal to 1/2 times the quantity of the sine of the sum of the angles, which would be, what would that be, 240? Okay, plus the sine of the difference of the angles. 165 minus 75 is 90 degrees. Now, we can find these because they're from our unit circle, and we should know these. The sine of 240 degrees is negative square root of 3 over 2. The sine of 90 degrees is 1. Now, I can just leave it as 1, or I could write it as 1 over 1 or 2 over 2 so that I can get a common denominator. So this would be, now I know it's negative 3 plus 2, I'm going to write 2 minus the square root of 3. That's all over my common denominator of 2 times a half is 4. And I think that's probably the simplest way to write that one. Now, using the idea of product to sum, we reverse this, we go from sum to products. The sum to product formula is here, and there's 4 of them again. And all these are a little bit different here. You can see that we just changed some signs in the middle here. We're taking the difference in the sum of cosines, the sum and the difference of sines. And we have these formulas here. Notice how similar they look. So I'm going to use, I'm not going to read through all this. I'm thinking you could probably read through that yourself. I'm going to write each expression as a product. Now this one is the sum of cosines, so I'm going to use formula 2 here. My x is 5x and my y is 2x. So this is 2 times the cosine. I take the sum, that would be 7x, and I divide by 2 times the cosine of the difference here, that's 5x minus 2x, that's 3x, and I divide by 2. And that's as far as I really need to go here. There's no really distributing, there's nothing I can do as far as factoring. That's my guy right there. Very similar, I'm going to use looks like formula 4 here to work part B. As you can see, it's a difference. So my x is beta, my y is 5 beta, so this is 2 times the cosine of the sum of beta and 5 beta, that'd be 6 beta divided by 2, which simplifies, as you can already tell. And then I'm going to have times the sine of the difference of the two, so that's beta minus 5 beta, that's negative 4 beta, all over 2, which again simplifies. I'm going to write this as 2 the cosine of 3 beta times the sine of negative 2 beta. And again, because sine is odd, with that negative there, I can bring that negative out in front and write this as negative 2 cosine 3 beta sine of 2 beta. That looks a little bit cooler. Okay. Alright, next thing up. Let's use one of these guys to find an exact value. And again, I'm going to use this. I'm not going to use some half angle or some sum or difference, although I most likely could. But this looks a whole lot like number 4 again here. The sine of 75 degrees minus the sine of 15 degrees. This would be my x, this would be my y. So according to this, this is 2 times the cosine of x plus y. That would be 90 divided by 2. The sine of x minus y, that would be x minus y 60 divided by 2. So this is 2 times the cosine of 45 degrees, sine of 30 degrees. So that's 2 times the square root of 2 over 2 and 1/2. So I get the square root of 2 over 2. And there's my answer, an exact value. Now I saved the best for last here in that I want to verify an identity. And as you can see, the left side is much more complicated looking than the right side. So I'm going to use the left side, and I'm going to use these formulas here to take these 2 expressions in the numerator and denominator that include a subtraction, and see if I can write these as products. Maybe something will cancel top and bottom. Maybe it'll simplify nicely. So the top one here, the cosine of 4x minus the cosine of 2x, that's number 1 here. This is going to be equal to, using this formula, negative 2, the sine. Now I have to add the angles. That would be 6x divided by 2, 3x, times the sine of the difference in the angles. 4x minus 2x is 2x divided by 2 is x. On the bottom, I'm going to take this one here, that would be formula 4, and I'm going to use formula 4 here, and I'm going to rewrite this as 2 times the cosine. Now I'm going to add the angles, so 2x and a 4x gives me 6x divided by 2 is 3x. And then the sine of the difference, 2x minus 4x is negative 2x divided by 2 would be the opposite of x. Now remember, I've already done this a couple of times, the sine of the opposite of x, sine is an odd function. So this is negative 2 sine 3x sine x in the numerator. I can bring this out as a negative and write this as the sine of x here. 2 cosine 3x, and then does that equal the tangent of 3x?
Well, look at this. The negative 2's cancel. The sine of x's cancel. I have sine 3x over cosine of 3x on the left side. And you can see it coming, I hope. And of course the sine of this angle over the cosine of the same angle is the tangent of that angle. And I get it to match the right side. And that identity is shown. So there's certainly a use to these. I don't put them in the same category as like the double angle formulas, but it would be useful to put these to memory and be able to use them as the opportunities arise.